Okay, now this most recent part of the discussion, there are other parts of it that I'll do after class. Put on video, okay? Um, in a coil or single loop or a bunch of loops, okay? See a bunch of loops of wire around this piece of PVC plastic, okay? The magnetic field you get is proportional to the current that you run through it. It goes back to the Biot-Savart law. Yeah. And then, we're moving in the direction of Ampere's law, which we've talked about. The Biot-Savart law, and again, I'll talk about what we did here, but just this. Okay. I prime, K prime times IDL cross unit vector in the direction of R divided by R squared. Which we've seen, and we've been using and talking about for a while, and we've looked at in lab, etc. Okay. In that case, your magnetic field is proportional to current. You just go back to the Biot-Savart law, and right there it is. Current times everything else. Okay. Direct proportionality just times the first power of the current for given configuration. Then we know that the rate of change of magnetic flux is equal to the potential difference created around a boundary, right? Okay. So your voltage, if you want to call that as a function of T, it's really, generally call it EMF, but I'll just use V of T for now, okay? Is not just proportional to the rate of change of magnetic flux, but it's equal and opposite to the rate of change of magnetic flux, okay? So proportionality constant here is -1. And for given configuration, the rate of change of magnetic flux is proportional to the rate of change in magnetic field. And the rate of change of your magnetic field is proportional, again, depending on configuration, to the rate of change in the current. Okay? So those are ideas you want to really lock in. And it comes down then to just your voltage is proportional to di dt. This is proportional to this. It equals negative partial derivative of magnetic flux with respect to time, which is proportional to this. And the proportionality constant between V of T and di dt is what we call L, and that's inductance. So when you have a circuit with a voltage, now this would indicate a constant voltage, but maybe with a switch that you can throw to see what happens, or an alternating voltage, this equation holds. Q over C is the voltage drop across the capacitor, because what is capacitance? It's a ratio of charge to potential difference, charge to voltage. So voltage is going to be charge divided by capacitance. Resistance times current, you're very familiar with. It's a voltage drop across the resistor. The voltage drop across the inductor is L di dt, where L is the inductance, which depends on, again, on the configuration of the loops and so forth. Okay, single loop has a bit of inductance, it's not much. So you have voltage drops around the circuit, and then the voltage goes up again from one plate to another. In this case, when you have an alternating current, well, you just think through how that works. And we're going to look at the equations. We're going to look at this equation in 3 special cases, where one case where the capacitor is missing, one case where the resistance is missing, and one case where the inductor is missing. And these equations are very, very easy to solve. Now, this itself is a second order equation, okay, with a non-homogeneous driving voltage. And that's a differential equation. Not everybody's had differential equations. We don't require it. You don't need it for this course. But the equations we get when we eliminate the capacitor, or when we eliminate the resistor, or when we eliminate the inductor, are very, very easy to solve using first semester calculus. So, I'm getting confused about what board I've got where. Okay, so here we have the equation again. Observing that your current is the rate of change of charge on the capacitor because you're moving charge from one plate to another. And it's the motion of that charge that creates the magnetic field, okay? The migration of charge. So I is dq dt, so that di dt is a second derivative of q with respect to t. So there's the equation as we would usually apply it, okay? Now, I remember being a little confused when I first saw this, and where to get the q's out of this. I had to think through what it meant. So I'm wanting to make that very explicit right now so you don't have to think as hard. So you think even harder about something else. Okay? All right, so let's just write down this equation more. Yes. Get over here, we'll see everything. What am I not gonna? Nothing yet, but it's gonna happen. Okay, we have L. And I'm going to stop writing the D's. I'm going to do LQ double prime plus RQ prime plus Q over C equals V of T. Fair enough? Now, you leave out the inductor. Then you get R Q prime plus Q over C equals, well, let's go ahead and let V of T equal 0 just for now. Okay. Okay, what does this correspond to? This corresponds to, we charge up the capacitor, put it in series with a resistor, and close the switch. So our circuit looks like this.
So I mismatched my negative sign. All that over. Take it. Again.
Say the initial charge is Q naught. Capacitance C, resistance R. There's our equation. How do you solve that equation? It's a separable equation. Solve it. Well, okay. You're going to have, how do I want to do it? Many ways to, okay, I'll use the dq dt again. Now, I already did this in class one time, and I had C in the wrong place. I had QC here, because it wasn't all there that day. Okay. I knew what I was supposed to get and I wasn't getting it. And I was too dumb to figure out what I'd done wrong. But you saw it. Hopefully you reviewed it. Solve it. You're going to have dq over q equals negative dt over rc. Solved equations like that in your first semester of calculus. If you've had differential equations you solved, well, you solved the equation, the whole equation. It might have been from a mechanical system instead of an LRC, you know, spring mass dash pot system. But it's the same equation, just different interpretation, different symbol. Okay. So you need to be able to solve that. Okay. Leave out the capacitor. You can draw it. You get L, Q. Well, I'm just going to write, okay, well, let's write LQ double prime plus RQ prime equals 0. Becomes L di dt plus Ri. You don't need Q because you don't have the capacitor. This equation is exactly the same as this equation, except that the coefficients are different, right? And the assumption is going to be a little different. Well, actually, I haven't thought through exactly how I want you to address this, so I'm going to go ahead and address it. I don't want to, I'm afraid I'd leave you hanging. Okay, so we're going to get di divided by r over L equals, well, no. I mean, that I could do that. You're going to get di over I equals negative r over L dt. And that should be clear. You get a negative r over here, divide both sides by L. There it is. You solve it. You integrate both sides. Fair enough? Should be simple. If you have to go to resource, make sure that that resource rings a bell in your head that won't be unrung anytime soon. Okay? Don't just take the resource, get the solution, and forget about it, which is the way AI makes us dumb. Okay? And the textbooks can make us dumb that way too. It's the way we use them. If you use it for short-term solution without integrating it into everything else, you don't learn much. Okay? So make sure that you write out a paragraph telling yourself what you need to know and refer to it when you need it. Don't refer back to a quick solution. Okay? Give yourself something to go on if you don't remember how to do this. I'll do it for you next time if you ask. I don't want you to do it yourself. Okay? So, now, most interesting, I find most interesting, and I'll solve this one for you. You get L U double prime plus Q over C equals 0. Now you can solve it by trial and error because what this tells you is that L Q double prime equals negative Q over C. So that Q double prime equals negative Q over LC. And you need to find a function whose second derivative is a negative multiple of itself. Right? What function has a second derivative that's a negative multiple of itself? Can't say it, but do you see what it is? It's a sine or a cosine, or e to the I theta. Second derivative proportional to itself. Sine, cosine, or e to the IT. Now, e to the IT is your standard sample or your standard trial function where you're solving a second order or higher order equation. You get a characteristic equation. It's e to the IRT, usually. You got to have a constant in there. But all I'm saying is the type of function is sine or cosine or an e to the IT. So that Q equal Q naught cosine of omega t plus phi. Sine and cosine are orthogonal functions. You would get linearly independent solutions if you substituted some linear combination of sine and cosine. Okay? A sine of omega t plus B cosine of omega t. You put those together and you get Q naught cosine of omega t plus phi. You have two constants, B and C, or A and B, whichever. Coefficients of the cosine and the sine. Put those together, you can get it, you can combine them into a cosine. A very simple way to do. Okay, something you should be very familiar with, hopefully are, but not difficult. Do you understand very basic trigonometry of these functions? Okay, so you plug that in and see what you get. See what you get for omega. Now, what ought the units of omega to be? Radians per second, right? It's an angular frequency, which gives you the frequency of your sine wave, cosine wave, whichever one you call it, okay? We usually call them sine waves because a sine wave is nothing but a cosine plus a phi, okay? And this 5 pi over 2 or negative pi over 2. Think about it. Don't worry about it though. Okay? You can always figure it out. Okay? That makes sense? What you're going to find, if you studied the mechanical system, pendulum, the oscillations of a pendulum. If you haven't had differential equations, you haven't. But just to make the connection, this system's just going to, I say oscillations of a pendulum, I'm doing up and down motion, mass on a spring or a low amplitude pendulum, okay? And all that we studied in first semester of simple harmonic motion. Right? We're just talking about simple harmonic motion. This equation is going to give us simple harmonic oscillation, which is under friction. Totally analogous to mass on a spring or low amplitude pendulum. So if you review the simple harmonic motion, which people did pretty well on compared to most classes, okay? Probably the best class performance I've seen on simple harmonic motion in decades, okay? I've had some pretty good classes over the decades. Somehow, either the ozone or something I did accidentally, or the fact that I kept stressing it all semester, seemed to have taken this time. I don't know what happened. You all must be particularly receptive to simple harmonic motion. That's pretty good. I think everybody's got a working knowledge of simple harmonic motion. That's what I'm saying. Use that working knowledge, solve this equation, and see the analogy. And what you're going to find is that the inductor, no, I drew it here somewhere. Maybe I didn't. I drew the circuit. But I didn't. I drew that one over there. Right here. Draw a circuit with an inductor and no voltage, because we're assuming voltage 0. Now we won't always assume it, but we really need some techniques of differential equations, not difficult techniques. If we have a simple voltage function with sine or cosine, it's not hard to solve it, but we won't do it. Because if you haven't had differential equations, you're going to be lost on it, okay? So we have an inductor and a capacitor. It's an initial charge Q naught and or current I naught. Well, if you've got that, you have the initial condition and you know exactly what your function is going to be. But what it's going to be is it's going to be a sinusoidal oscillation. How does that work? Well, you got charge in the capacitor. Let's say you got no current. You just got charge in the capacitor. You got a charged up capacitor. You put this in a circuit, you've got a switch here. You close the switch and the capacitor starts creating a current through the inductor. Okay? You don't get an instantaneous current. Because if you get an instantaneous current, well, the current through the inductor is going to create a magnetic field within the inductor that fights the current that the capacitor is trying to push through. just like what we said before, if you got a current inductor and it falls to zero instantly, you have infinite magnetic field, which creates infinite current back in it and everything blows up within a block. Okay, makes sense? So you can't have an infinite rate of change of charge or of current through an inductor. Same thing applies with a capacitor. You throw that switch, the inductor starts trying to charge very fast, but it creates a back magnetic field that prevents that. Increases slowly. Okay? Sinusoidally in some way, think about it. And then the capacitor eventually gets rid of all its charge, and now the inductor has all this current running through it. It can't drop to zero instantly. So the current keeps going, it starts decreasing, but that charges the capacitor up again. And then it all starts over. The capacitor gets completely charged, the inductor gets rid of its current, and now the capacitor charges up the inductor again, which in turn then charges the capacitor. It keeps going back and forth forever if you have a superconducting circuit. Okay? Pretty interesting. It's pretty neat. So think about that. Try to understand the details. Try to understand this as completely as possible. It's a big thing. It's like simple harmonic motion mechanical system. Okay. We started class. Before we did the stuff I went over here about the differential equations and so forth, equations for LRC circuits or LC circuits, LR circuits, or RC circuits. I posed the question, if you had 1 kilogram of your choice of copper, silver, gold, or any other conductor that you might wish to use, how would you configure that kilogram of stuff, assuming you've got the ability to shape it any way you want to? How would you configure it to produce the maximum magnetic field given a 12-volt source? Now, everybody already seen Helmholtz coils, so you could choose to do what you've already seen, but as people come up with their ideas, we came up with various ideas. People reasoned out, well, it'd be some kind of, you'd want to use rings because you get the field at the middle of the ring and so forth and all through it. Similar to what you get with the Helmholtz coils. And they picked up a lot of stuff about the Helmholtz coils, measured the magnetic fields within it and stuff, and then looked at alternating circuits produced by a magnet rotating within the coils. Just magnets suspended from string of rubber bands and oscillating, circling at different speeds. So people are kind of familiar with that configuration. Then they said maybe like an atom, with rings like this and rings like this and rings like this. And said, well, you want to think about the directions of the fields. Is that going to work? And somebody said a sphere. But I wonder, how would a spherical, you make a sphere out of loops. You just keep making loops around a sphere. What would you have? Would you have something useful? How would that give you a magnetic field? What kind of magnetic field would it give you? Can you quantify it? Or can you at least do it in symbols? Okay, so there's a whole discussion there. We spent quite a bit of time discussing this, and everybody had some good ideas and good thoughts. So I'd like everybody to pursue those thoughts. Okay, now I move that then to a bunch of coils, a continuous bunch of coils. And I have one somewhere right here, my left hand. Okay, now this is just a roll of magnet wire looped around this piece of 1.5 PVC. So we got a bunch of loops there. Okay, is that a good way to produce a maximal magnetic field? Now, one thing I didn't mention was the use of some kind of a metal core to enhance the magnetic field. Um, but once you get the configuration, then you can put uh, some kind of magnetic material inside to multiply the magnetic field by maybe up to 100 times. So we can talk about that later. We haven't talked about that yet. We're looking at just the geometry of this thing. Okay, if you got a bunch of coils continuous, that means these loops here go around and they're connected to one another, just kind of a helix, but a very tight helix. I'm just giving you general idea here. You got a path here, okay? It's a rectangular path. It extends from, let's say, through any part of this configuration. It extends like this way, and then straight down through the coils down to the inside, and then back this way, and then comes back outside and joins up here. So it's like a rectangle that cuts this thing. And if we actually cut this thing, which we don't want to do, but if we actually cut the thing, what we're going to see within that rectangle is just the cross sections of the various wires. Okay? So we got N coils cutting the interior of the path. In this case, N would be 5, but in general, we just mean N coils cutting the interior of the path. And I'll also add over some length, over some distance. So we got some idea what the dimensions of this rectangle might be. Ampere's law says that the integral of the magnetic field dotted with your length increment is going to be proportional to the number of coils cut by this thing times the current in a given coil. Okay. I'll observe that if the coils are going in this direction, then the magnetic field is going to be in this direction. Okay? So that the magnetic field on the inside part, let's say this is a part of the path that's inside the cylinder. Okay? If you're integrating in this direction, then you would just multiply this length by the average magnetic field. It turns out that for a coil like this, which is a solenoid, that's what you call this thing, the field doesn't vary much within the cylinder, at least as long as it's not real close to the ends of the loop. Okay, so you pretty much have a constant. I said the magnetic field doesn't vary much inside here. You have a pretty constant magnetic field here, and it's parallel to the path. When you're going up here or down here, actually I've got it integrating in this direction, but that's all right. When you're on this part of the path or this part of the path, what's your angle with the magnetic field? And when you're in this part of the path, what is it? We can also observe that we can make this thing as long as we want. So we can remove this path as far from the coil as we wish to. Put all that together and you learn something. Okay? So I'm just going to give you the outline of Ampere's law. It's the integral of the magnetic field dotted with the increment of displacement around this loop. It's proportional, again, to the number of that you cut with this rectangle times the current is common to every loop. And I also mentioned that you remember that Biot-Savart law, which you should be pretty familiar with by now. There it is. Review that a little bit and ask yourself some questions about what the directions of the field ought to be here, or your R vectors, what are you crossing with what, et cetera. Okay, sort that out. Use AI. Okay, now I don't mean use AI to get the answer and just write it down without thinking. I mean, use AI to teach you and even test you on whether you understand this. Okay? Use it in a constructive manner so that when you come in next time, we can talk about Ampere's law without me having to explain it to you any further than I already have. And we can use it to maybe evaluate the relative merits of this configuration as far as getting your maximum magnetic field versus a single loop or a bunch of loops close together or two sets of loops like the Helmholtz coils or something else that you might think of, a couple of rings, okay? The thing I'll tell you is you have to balance the effect of resistance with the number of loops. If you're making loops, you're putting this copper into loops, you got to figure out how thick do you want the copper. The thicker it is and the shorter it is, the less its resistance and the more current you're going to get from the 12-volt source. But of course, you only have that current once. Whereas if you divide it into a bunch of loops, I mean, draw it out into a long wire and make a lot of loops, well, resistance is going to go up, so the current's going to go down, but you're going to get more loops, so you're going to get more, the more loops is going to tend to give you more field, and the more resistance is going to tend to get you less current. So how does that balance out? So this very interesting problem. See what you can do about it, and don't let AI solve the problem for you. Let AI explain Ampere's law to you, and don't ask it any more than that. Use your own imagination, because in a world of AI, which we're in already, asking the thing to give you the answer that you don't really understand and haven't worked out for yourself is not going to develop the kind of curiosity and creativity and the qualities that will make you valuable as someone who can work with AI. That's a prediction. It's a fairly common prediction. It's kind of been my take on it for some time, but I'm seeing that other people have finally picked up on what I've been thinking. Well, seriously, it's kind of an obvious idea, and don't know how it's going to play out. We don't know exactly how AI is going to develop, but right now it might be something close to a consensus best guess as to how AI is going to interact in a positive way with humanity. There are all kinds of negative ways if we screw it up and let it make us all dumb, which it's doing a good job of right now, according to many sources. Okay? Don't let it make you dumb. Let it make you smart. Figure out how to let you make it. Figure out how to use it so it makes you smart. Downside of using it so that it makes you smart is it takes a lot of work. You got to work hard. You got to challenge yourself. And people tend to back off from hard work and challenge. If you develop enough curiosity, then you're going to dive into it spontaneously without having to force yourself. Not sure how you develop curiosity. Hopefully you've already got some and kind of enhance that. Okay, now I'm just kind of rambling. So that's the end of that for today. But good luck with these problems. Okay, there are going to be more.